Anyway, thank you everybody for coming tonight. My name is Ben. I'm a staff engineer here at SpotHero, and we're going to be talking about search. So before we get started, I want to just say a couple things. If you're looking for the restroom, the men's restroom is just straight back on the left here of these refrigerators, if you're in my orientation. And if you're looking for the women's restroom, you're going to go through this corridor in the back here, and then take the left and go all the way to the back of the hallway. As you probably have already seen, we've got beer, drinks, pizza, water. You can also, the refrigerator that says communal, feel free to pop in there and grab anything you want. We've got snacks, cereal, whatever. Make yourself at home while you're here. So yeah, we're really excited to host you guys today. We love Go here. You'll probably get that from this presentation. And one of the things I want to open with, I'm also going to close this. We are hiring. So if you like what you hear in this presentation, if you think these problems sound exciting, please apply. We have 9 open positions right now, everything from just sort of day-to-day engineer to senior engineer to director of engineering. So really all skill levels should apply. We'd love to talk to you. We really need Go engineers. So, but before we start, who am I? Essentially, I've done a little bit of everything in my career. I started my career in embedded systems, doing some hardware. I worked in computer vision, natural language. I worked on web backends at SpotHero, and I've done a lot of operations work as well. One of the things I'm most proud about is my work with the open source community, as well as doing some maintenance work, specifically with Kubernetes, Helm, and Airflow. And this is actually how I made my introduction to Go, was by actually working with Kubernetes a couple of years ago when it was still fairly early on, reading the code and just finding myself really impressed with what I was seeing and the simplicity, and in my opinion, the elegance of how that code came together. And then when I started to look at these other libraries, I saw that they looked similar, and I thought to myself, maybe there's something to this language. And then finally, I'm also a Udacity data engineering instructor. So if you're interested in data engineering, if you're looking to change your career, or you're just interested in how data engineering works, I'll send you slides out later. You can click this link. It's my personal referral link. You'll get pretty good discount at the top. So that's all I got to say about that. And one more thing I want to say: if you have any questions during this presentation, if you are concerned or you're just confused, feel free to interrupt me. This is actually my first time giving this talk. I'm really excited about it. I want to give this talk a few more times. So I'm very open to feedback, positive, critical, whatever it is. Okay. So about a year ago, a little over a year ago, we had this really exciting opportunity, right? We're a small company relative to a company like Google, right? We have about a 50-person engineering team today. And Google said, hey, we want to present with you guys at CES Las Vegas. We're making some updates to Android Auto, to Google Assistant. We want to make it so that we can show off in a car. A user could say, hey, Google, book parking at Millennium Park Garage on May 30th from 3 p.m. to 6 p.m. And then if you have a credit card set up in Google Wallet, you can go ahead and do it. Pretty cool stuff, right? And we were super excited about it. But there was just one problem. There were actually a couple of problems, which you'll see some of the stuff on the slide, the problem. So at the time, we had actually been experiencing some stability issues. So, I mean, we were up most of the time, but we were running into some real growth problems. So we were having a lot of success as a company. We were bringing on a lot of new customers, and we were starting to sort of see the limits of our Python Django application. So if you're not familiar with Python Django, if you might be familiar with Ruby on Rails, it's a similar type of framework for Python. In any case, we had a monolithic application, one giant app. At this point, it's probably about 6 years old, and there's many layers of history code in that code base, right? And so it was relying on 3 technologies for some of the places where we were having problems getting speed and scalability. We used RabbitMQ, which is this orange logo over here, with a tool called Celery for asynchronous operations. Rabbit is, and actually continues to be, a real pain point for us. Real stability problem for us. We used Redis for caching, but as you'll find out shortly, we also performed Lua calculations in Redis. So it was more than just a cache for us. It was actually a place where we ran code that was in our search path for our actual service. And then we have Postgres. I actually don't have anything, I really have nothing negative to say about Postgres, Redis, for what it's worth. These are amazing tools. They're really well designed. But the way that we were using Postgres, we were making way too many queries. We were really pushing it to its limit. So we knew that we had this problem, and we knew that if we were going to work with a company like Google, we really needed to up our game, right? If they went out to Las Vegas CES and we were down, or we made them look bad, that wasn't going to leave a good taste in their mouth, and it was going to mean that we missed this huge opportunity, right? We're a small company. We want to be a bigger company. And the only way you can really do that is by, impressing a big partner and being a good partner to your existing customers. So the first thing we said we needed to do was measure, right? The biggest problem we had was, as a company, we knew we had a problem, but there wasn't a specific metric that we could point to say, hey, this proves that we're having a problem, or this is the point in the code that's really slow. We really just had sort of this gut instinct. So we created a production-like environment. We duplicated all these technologies, basically more or less just think of copy pasting, or at the time it was on ECS deployment, and cloned our Redis, cloned our Postgres, cloned our RabbitMQ. Everything was exactly the same size, and so on and so forth. And then we set up a tool called Gatling to run load tests. And this load test tool actually would read out the last 24 hours of production traffic from Sumo, our log provider, and just play it back at different frequencies. So this was as close as we thought we could get in a pretty short time frame to reproducing production-like traffic. And it turns out things didn't go so well. We thought, well, we knew things aren't going to go well, but if we throw enough money at the problem, we can probably say hit 1,000 requests. We think we can do that. Again, remember we had no data. Turns out the best we could do was 150 requests per second. Now, I understand that sort of without context about what we're actually doing, that number could be impressive or it could be not impressive. But I just want to remind everybody, this is the most common operation on our phone. So this number should be a lot higher. And this was, no matter how much hardware we put at it, at this problem, we couldn't get it to go any higher. So we're kind of sweating bullets, right? That's with 150 web servers. That's not 150 containers, that's 150 nodes. You're running a C5 18XL Postgres node in Amazon. If you don't know what that is, don't worry about it. Just know it's the largest, at least at the time, they may have a larger one now. This was the largest compute node that Amazon offers. So we can't go any higher than that. And we're running an R34XL Redis node, which is also pretty sizable and pretty expensive. Okay. And this 150 requests per second, I say this is the best we can do, but I don't even know if you can really say it was a success, because only 93% of our requests even got a response. 7% of them failed. And those requests that did respond came back at 16-second mean response time. And just for context, if you go here, I'll actually jump out here. If you go to our search page, if you go to this search page, and I'm just going to refresh real quick. What's happening as this page loads, you'll kind of see the center loads, then a bunch of other spots load. That's because we're making 5 to 6 asynchronous requests. Okay, so it's not just one request with all the data, it's 5 or 6 asynchronous requests. So if I'm going to jump back to the presentation here. So when we talk about a 16-second mean response time, multiply that by 5 or 6. You're going to have some very, very not happy customers. And there's also the chance that they fall into that 7% request failure. So why was this so slow? What was the thing that was driving the slowness? Well, after doing all the instrumentation and research, it turns out that it was search. It's, like I said, far and away the #1 thing that we do on SpotHero. Basically any kind of integration with SpotHero hits search at some point. So when we talk about search, what do we actually mean? Most people, when they hear us talk about search, they think of text search. They think of Elasticsearch. They think of Google. That's not what we're talking about. Search at SpotHero is specifically inventory. So when we talk about inventory, we actually mean physical spots at a parking facility, right? How many slots can we put a car in? The other side of it is pricing. This is an internal dashboard view. You don't need to recognize this, but essentially this is just showing all the different combinations of ways that we can come up with a price. Okay, so we take inventory and pricing, we figure out those two things, and we return that result to the user. That's what we mean when we say search. I mean, thing is most people then ask the next question, well, how could that possibly be that difficult? Well, it turns out that there are a large number of checks involved in both of these processes. So if we talk about inventory, we have to answer a couple of questions. The first is, well, for the given time period, start and end time, how many actual parking spots do you have? So that's not just like a simple lookup in a database table. We have to also go and see, well, how many reservations happened within that time frame, right? And kind of correlate that. There's also the question of hours of operation. So is the facility even open? Okay, well, that's usually easy enough to answer, but then you get this added additional complexity of something called overnight parking. So let's say you're parking in like a lot downtown here. They may be closed from 10 p.m. to 2 in the morning, but you can, if you park, let's say at 8 p.m. and you leave at 5 a.m., so you're in before they close and you're out after they open, you're allowed to park overnight. So we have to handle these kinds of weird edge cases. And I'm not going to go through all of them, but I just kind of want to give you guys an example. And then, there's also special events. So we might modify the amount of inventory. We might have more or less inventory based on like the Cubs game at Wrigley Field or some special event at a theater downtown here. Or we might just have to take it offline because they want to sell all their own inventory. They don't want to work with us. Or maybe it's blocked, like the Chicago Marathon. Maybe it's like you can't access that facility. And so we're not going to go through all this, but just know that we can come up with this very complex representation of how to actually, how do you programmatically create an answer to this question? And the answer is you have to do a lot of time-based calculations. And as you all probably know as developers, time-based calculations are not always the easiest. And we're not even talking about just time, we're talking about periods. So start and end, and so on and so forth. So if that wasn't complex enough, you also have pricing calculation. Our pricing calculation is an NP hard problem, believe it or not. So again, we have to figure out what do we charge this person for a start and an end time. Are there any events? Events modify price. So again, like if you are someone who owns an apartment or a condo in Wrigley Field, you might want to rent out your parking spot for twice as much during a Cubs game, right? And then this is where really the NP hard part comes in. Well, you guys ever look at like a rate board at a parking garage? I'm actually gonna pull up a picture here. And they have these crazy boards, you pull into a parking garage, where it's like you have to do a whole bunch of mental math and gymnastics to figure out, well, how much are they actually gonna charge me if I park, right? Well, if I park somewhere for 10 hours, or for 9 hours, are they gonna charge me a 9-hour rate? Are they going to charge me 9 times the 1-hour rate, 3 times the 3-hour rate? What about a 5-hour rate, 4-hour rate? And all of those things are potential solutions to the problem, right? But which one is the best solution? And so we have this really, really complex set of business rules that help us decide this. So yeah, that's a hard problem. And so with sort of the concept of what we're doing in mind, I'm going to talk about what the team did 6 years ago when the original algorithm was created. So I said, okay, wow, there's a lot of stuff we got to do, right? This is really complicated. We're using Python. We've got all these problems with what happens if we have 10 web requests coming at the same time? How do we make sure that we don't oversell a facility, right? Someone searches and then they book and they search. I want to make sure that I decrement before I return that result. And so they came upon Redis, and they said, well, we're already using Redis as a cache. What if we just use Lua script to use our cache data to calculate inventory and potentially pricing, and then return that to the users? Because Redis is single-threaded, by definition, as those requests come in, we're not going to have any issues, with atomicity. So the team did this, and at the scale they were at 6 years ago, this was a great solution. It worked really well, and up until probably about 2 years ago, really people hadn't thought twice about it. But it turns out, as you probably have guessed, it's turned into a big problem. So first thing, we were saturating network on our Redis node. This is actually why we were running such a huge Redis node. We were saturating a 10 gigabit Ethernet card. To me, that's amazing. I think it's a big deal. And we were able to sort of remove some of the data from our responses and trim it down, but we were still super close. So we were worried about it. The other thing is when you use Lua scripting, the Lua script has no concept of a cluster. It doesn't know that there might be 15 nodes in your Redis cluster, so we were stuck on a single node Redis cluster. So it's not like we could just buy hardware to get out of this problem. the design of how this algorithm was built meant that we were stuck on one node. And then we didn't really have a cache warming strategy. The complexity of these algorithms meant that there was not really a way for us to just pre-build the cache. So if a developer accidentally went in and changed the data model without basically upping the version of the cache, or they modified it in some way, or accidentally dropped a portion of the cache, we could experience these really painful rolling outages. Some of the most stressful hours of my time at SpotHero were happening. And then finally, it's hard to develop, maintain, and test. These are basically, these Lua scripts are just giant, multi-line strings in our Python code. And no one, basically you've got Lua inside of Python. It's just kind of a big mess. So, and then in addition to this, we talked about Redis a lot, but we were pushing Postgres to its limit. It's not important that you necessarily see the details here, but this is just like the top portion of a Postgres trace in Jaeger. And so you can see, if you look really closely here, if you follow that red dot on the screen, there are thousands of requests to Postgres for one search request. This is why, in part, we were pushing Postgres to its limit. So we basically, just to summarize again, we had some serious problems. We knew we had to do something about it. We knew that at this point, that it really called for a full redesign of this portion of our functionality. We didn't want to rewrite our entire monolith all at once, but we needed to focus on specific. So we studied the code and tried to figure out what are the things that we're missing, or the last team missed, or that have happened over the past years that might help us when we go forward and rebuild this. First thing we figured out was that, hey, this Python really just treats this huge complex thing as one giant function call. So if you look at this gray box on the left here that says search, like that's literally what we thought. When we talked about search a year ago, we would just say, all I meant, just search. But actually, it's all these things on the right. It's these 8 boxes, these discrete components. And they're totally discrete. Not only that, but they're not even linked. They're completely independent things. Like if I calculate the hours of operation for a facility, that has no bearing whatsoever on the existing purchases. I can calculate those things at the same time. Problem. Likewise, the state of these things never changes, like maybe once a day at most. So they're more or less fixed. The only exception to that is existing purchases. Obviously, as people buy parking, we need to update that model. And then finally, this is the description of essentially one facility's search result. So how much should we charge and how much inventory is available? And this calculation for this set of calculations can be done independently for every facility, of which there are thousands of platforms. So what does that mean? Well, it means that this entire problem space is massively parallelizable. Every single thing is independent of every other service. This is what the legacy algorithm did on a facility basis. Calculated one thing, then it calculated the next thing, then it calculated the next thing, and so on and so forth. You can see we have over here time equals 0. So how long does it take? Well, it takes as long as it takes to do each of these things serially. Well, and we realized, what could we do? Well, we could do this. Basically, the execution time, because everything can be parallelized or done concurrently, basically the length of time it takes to perform this operation is the length of whatever the law is. So this in itself was a big realization. We also realized because the data models don't change very often, we could leverage Kafka to basically create an application that's downstream of Kafka to have an in-memory data set. So the new search that we were going to build wouldn't actually necessarily need to be backed by a traditional database like Postgres. So we came up with a design that looks something like this. We have our legacy database here. We're going to use Kafka Connect. Kafka Connect will use SQL to query our monolith Postgres database, and then push database changes as Kafka events into the Kafka topic, Kafka topics. And then our new search service, which, I'm sorry, it says availability. Internally, we refer to search as availability. But our new service would then basically on boot pull all of the data out of Kafka, and then as soon as it's done bootstrapping, subscribe to all the new events on all those topics, so that basically the state of the application is completely in. And so, based on this, our first instinct was, well, yeah, great. We have a great problem. We have a great problem here. We can parallelize a solution to this really easily, because each one of these pins on the map, each one of these parking facilities is completely independent. we can parallelize it. And this is essentially like what that would look like, right? We have each one of these boxes. Within the boxes could be independent. We thought, I used to work in embedded computing. I did work with GPUs, CUDA and Thrust, and I said, well, this seems like. I know that probably sounds pretty crazy, right? We're a web company. We're not like doing machine learning or computer vision or anything like that. Like, why in the world would we do that? It's a good question. And there's a second half of the story, so just sit tight. So we had built a POC, and this POC worked really well. We were really impressed. One GPU node could push 100 requests per second. Remember that 150 nodes was 150 requests per second. So we put this POC together in a matter of weeks, and the whole team was super excited. And the average response time dropped from 16 seconds to 50 milliseconds. I'm just going to put that in context. This is 150 little boxes. 150 boxes, 150 nodes could do 150 requests per second, 100 facilities per request, and 7% of the requests. One node was now doing 100 requests per second, calculating the results for 6,000 facilities. 0 failures, 50 milliseconds. Pretty good results. And then we said, okay, great, we're gonna do this. We're gonna ship this code. We need a web server. We don't want to write HTTP code C++. That's a disaster. We don't want to write any more C++ than we have to. We're going to use Go and expose it, you know. And so we looked at we looked at Go, and we said all of our favorite tools are written in this. I kind of alluded to this earlier. We use Jaeger, Prometheus, Kubernetes, Traffic Helm, like basically all the sort of like headline Go tools. We love them all. This is really the inspiration for why we started to use Go. And so we went to management and said, we really want to do this. We've had such a good experience. These are the reasons why we think we should use Go. So the first one, concurrency support deeply integrated language. You've all heard of the Go routine. You're at a Go meetup. This is usually the first thing you hear about Go. And we thought, given the problem that we had, this language is the perfect. We also like that it was statically typed and compiled and fast garbage collection. Versus Python, which is not these things. It also, and this is actually my personal favorite thing about Go. If you ask me why do I like Go, this is actually the thing I'll talk about. I'll talk you off for like half hour about just this one topic. I love that Go makes really a lot of opinionated decisions and just eliminates this whole class of bike-shedding arguments. I think I probably in my career have spent more time arguing with people about sort of these benign little things like formatting or tabs versus spaces than I'd like to admit. And so I love that Go just sort of like says, we're not going to do this. We're just going to make those decisions. Sometimes I don't like those decisions, but tough luck. And then, of course, Go has some pretty amazing community support and library availability. And the quality of the libraries that are out there are, honestly, I think, given the age of the ecosystem, pretty stunning for how good they are. And then, of course, that HTTP, you've all seen that, used it if you haven't. This is, I think, one of the nicest things about Go when you're first getting started if you're doing web development. Fantastic, well-designed. And I could keep going. I'd probably add 100 more things to this list, but this is what came to mind when I was building this slide. So I think you get the point. Go with the first. And so we went off and built this web server. We were having a lot of luck with Go. The team was excited about it. Everything went basically according to plan, even ahead of plan with Go. But at the same time, we started to run into some problems with the C++ GPGPU thing that we were talking about earlier. While the POC had initially started off really, really well, we were kind of in this category down here. I don't know if you guys have heard this quote, you know, there's the known knowns, the known unknowns, and the unknown unknowns, right? It's a famous quote. We were in the unknown unknown. That last 20% of the problem that we hadn't solved yet, turns out that 20% really, really poorly fit for our GPU. And so we ended up basically saying this isn't working. As much as we hated to, we had invested a good amount of time into our code was ballooning. Kubernetes and device plugin API where our GPUs would come in through were super unstable. We just had nodes go offline and we couldn't recover them. We were super concerned. So my colleagues and I said we need to do something. Otherwise, this project's we're gonna get in a lot of trouble here. We've got this tight deadline. We got the CES thing coming up. We've got some important partnerships. So we said let's just see if we can take what we've learned by writing this purely Go application. And We were all super surprised how quickly it came together. We basically moved our POC from C++ to Go with tests. I'm not exaggerating. You can have Brian back there. He'll confirm this is not a false story. And the results are really good. It was fast. I'll give you specific numbers here shortly. And actually, to our surprise, leadership was like, "This is awesome. I'm so glad we're not using C++ anymore. This is the best news we've ever heard. Those GPU nodes cost like $900 a month. So glad we're not running those anymore." It was across the board. Everybody was basically great. As fast as you can do C++, please do. Yeah. So the question was, you moved the calculations you were doing in C++ into the GPU, and it was just in performant, or what happened? So the answer to that question is actually that we basically took the data structures that we had developed and the way that we thought about the problem and moved them. When we talk about calculating the results in the GPU, we were doing it, we were trying to generate cache. So we were actually using the GPU to calculate the results for every facility in SpotHero system. So we were calculating parking results for the entire globe, a handful of clock cycles. So for thousands of parking. Like when you search on, like, let's say it's Uber or SpotHero or whatever, when you search on that map, typically people are going to do a lat-long calculation and say, I want all the things within a certain distance. The GPU didn't do that, but I don't care about that. I'm so powerful, I can do all the things, all of them. We moved it to Go. We changed it so that it's more traditional search. It says the user wants to look in this location, this latitude and longitude, only look at facilities, parking facilities within this distance. So the Go is actually more performance in terms of just as far as like what the end user sees. The Go is actually a lot faster. It's faster than 50 milliseconds. We'll get there shortly. But the difference is that it's not calculating as much. So the problem space it's looking at is, can I answer your question? So this real quick, this is basically what we, probably a little bit washed out, so I'm sorry about that, guys. But essentially, this is what we ended up building. This is actually a diagram of how the application ended up getting built in Go. It's fairly straightforward. We have a handful of what we call internally handlers. So you might, if you can see this, I'm sorry if it's washed out, but if you remember from those earlier slides where I had those different colored boxes, we talked about inventory, blackouts, grayouts, yada, yada, yada. That's actually, it's a one-to-one mapping for each one of those handlers, okay? And so we ingest from Kafka. These handlers then contain the data. And then down here, we have this availability service or the search service, which actually then calls each one of these handlers, then takes the results, puts it together, and sends out the response to the caller. So it's actually a very simple architecture. What's really exciting about this for us as a company is that in the future, in the past, because this was all one thing, making any change was a nightmare. Like people were scared to touch the code because it was one giant thing. And now it's super easy for us to add and remove different components, to experiment with new algorithms, change our pricing without stressing out about what that would look like, because it's very much flat in structure now with all these things. And actually, one thing I want to mention about this that's really cool, and I think Go actually really encourages that design I was just talking about, because of the fact that Go rewards, makes concurrency so easy, you're really like encouraged to essentially say, well, I don't want to have one big function. What if I could have two Go routines working on something at the same time, potentially at the same time if they get parallelized? You're going to get rewarded for doing that in terms of speed, right? So this is actually one of the ways where I think Go is a real big addition for us as a company. So how does this actually work? The process is super simple. Essentially, the first thing we do, we have a library that we built internally that is open source called GeoCollection, which essentially, given a latitude and longitude, we'll go ahead and find all nearby parking facilities. So here I've drawn this circle around all these parking spots. We'll say, hey, these are all the spots that we need to look at. Then once we've done that, for every single facility, we spawn a Go routine, right? And say, within each Go routine, calculate inventory and pricing. So go ahead and so these are all those colored boxes I was talking about. Each one of these is a handler. So each one of these things goes off and actually does the calculation for its specific responsibility. Then finally, those results coalesced into a JSON return. That's all there is to it. I mean, there's obviously more to the actual algorithms, but as far as what you need to understand as a developer coming into the system, that's the top level. So I want to just take a moment here, because one of the reasons that we were so successful with Go is that we built on the foundation of a bunch of really awesome open libraries. So because this is a Go meetup, I want to talk about a handful of the libraries that we think are some of our favorites. First one is Zap. Zap is a really great library for logging. The tools that ship out of the box with Go are good, but for our specific use case, we wanted fast, structured logging. We think that Uber has done a fantastic job with that. GorillaMux. So if you've used HTTP ServeMux, you may or may not be a fan of sort of just using straight regexes. For our specific use case, we really wanted sort of nice tool. SPF 13, Viper, Cobra, and T-Flag. Most people have probably heard of these for apply environment variables, but I really love this tool. I think they did a great job defining it. This is every single Go application on Spot has these three things integrated with them. Structure testify. So you don't have, again, one of these things, you don't have to use it if you don't want to, but we really like all the additional assertions and mocking functionality come out of the box with testify. We think that's a really nice tool. We use Jaeger. I love the Jaeger library. I think it's really easy to use and well thought out. I think actually that if you look at the Jaeger server that Uber has built, or specifically Yuri and his team has built over at Uber, they've done a really nice job. I think it's one of the inspirations we used when we were getting started with Go for what well-structured Go should be outside of Kubernetes. Then Prometheus uses gRPC, which is kind of cool. So it's kind of a fun application to look at if you've never done that before and want to see how they end up using that tool. And then finally, Sarama. So Sarama is a great tool. We love it. We love that it uses what we consider a more idiomatic and Go native approach to interacting with Kafka versus some of the competing libraries out there which have C binding. So with that in mind, after we built all this tooling and we had all these fantastic results, which we're going to get to in a second, we thought some of the work we've done could be open. So I also want to take this meetup as a second here to announce, or at least promote, some of the things that we built. We'd love if you guys take a look at these. Again, this will be posted so you can get the links for this afterwards. The first thing that we built is something called periodic. I was actually talking with my colleague Brian this morning about this talk and saying actually that we may be more proud of what's in source library than what's actually in search, and we're very proud of search. But there's a lot of really cool time windowing utilities in this open source library. So remember earlier we were talking about inventory, and we have a start and an end, and we have to figure out whether or not, like, how many reservations overlap. There's a lot of complex sort of time windowing functions involved in that, and this library solves that really easy fashion. So you can say if I have a floating period that has a start time at say 5 in the morning, ends at 9 o'clock at night, and it applies say Monday through Sunday with UTC time, and then I have another time period with start and end. Does this floating period contain? Do they intersect? Are they completely independent of each other? So this can be super useful if you're doing something like hours of operation. The other thing it does, which I think is really cool, is fast collection lookups. So let's say that you want to group a bunch of related structs or values to a time period, right? You've got a bunch of data that belongs in a specific start, right? Well, periodic has the ability to say you can associate groupings of objects to that specific time period. So that's what we're doing here. We're actually creating a time period start and a time period end. And then we're creating a period collection, and then we're inserting those things. And then we can say, hey, given that period that we've defined here, find any intersecting data with the other period, which is pretty neat. This is actually how we quickly do lookups for, say, like, I want all the reservations that happen between 3 p.m. on a Monday and 4 p.m. on a Tuesday. If you think about, like, what data structures would you use? It's actually kind of complex. And so this actually runs at worst O(n) time, linear time. On average, it's logarithmic because it's using a balanced binary tree, specifically a red-black tree. So this is something we built in-house, and we have tested the hell out of it. This is literally the beating heart of how search works. So this is not just, if you're worried about abandonment or anything like that, as long as SpotHero is in business, this library will be somewhere. So believe us, we care a lot about it. So check it out. This is something that you might be interested in. The other thing that we're excited about is the library we call tools. It's not very imaginative of a name. It's a collection of utilities, essentially, things that don't stand alone in the library. We have utilities for HTTP, durability, Kafka, SQL. But I just really quickly wanted to show you something that we built here. So if you really just want to quickly, if you you to go, if you've never used it before, just want to kind of potentially experiment with what a production web server might look like. This is also open source. You can see about how SpotHero thinks about what a production web server should look like by essentially configuring this HTTP config and then creating the server command and executing it. You're going to get a web server that has integrations with Jaeger, Prometheus, Snap, and a bunch of middleware that will add sort of what we consider best practices like intercept HTTP, HTTP outgoing response, and put all that on the logs and so on and so on. So take a look at that. All my personal projects, I use this to help build it, but I think it's kind of a nice little wrapper around the things that we've done here. Another thing that I think is kind of cool is if you use Zap, you may have noticed that one of the difficult things about it is that Uber doesn't provide a good way to pass around the logger with fields already on the log. So like every time you write a log, you want to put out, say, the HTTP response code or the path, right? If it's in the path of a HTTP request. Well, you can't do that out of the box with Zap unless you keep adding it every single place. So we built a little wrapper in our tools library that actually uses the Go context to essentially store the logger. So you can say, hey, I want to, on every single one of my logs, I want to have an HTTP status code and an HTTP path. So you can call this function log.withContext and pass in those fields that you want to log. And it will give you back context with that logger embedded inside of it. And then from there on, whenever you call that logger, then you log, those fields will be added to it. So again, when talking in the context of, talking about an HTTP request, anything in that path of that HTTP request will now have these things logged along. So what would this look like if I actually called my function? You would end up with a log line that looks something like this. So you always get to see the level of timestamp in the caller. You can see we've got the message on the log statement. We've got this message here. But we also have HTTP status code and path, even though that wasn't added explicitly here. It's a pretty nice little utility. Truth be told, if you wanted to just build that on your own, go ahead and have a look. Take it for yourself. If you don't want the whole tools library, I actually think this is a nice little thing to have. And then finally, geo-collection. So remember earlier we were talking about periodic, and we could say you can look up a group of objects related to a time period. We did the same thing with geo lookups. So we actually wrapped Google's S2 library. If you haven't heard of that, S2 is actually what Google uses behind the scenes on Google Maps. It is a really neat library. It's a talk all into itself, so I'm not going to go into too much detail. But essentially, you can say, hey, given a latitude and longitude, find any object that's within a certain distance of that latitude and longitude. Okay, so here, I'm creating a couple of locations. I'm giving a latitude and longitude for downtown Chicago and another one for downtown Manhattan, right? And if I put that inside of my geo collection, and then I do a lookup, say, give me the items within a certain distance, I pass in a latitude and longitude, and I say, give me all the items within 1,000 meters. Well, this lat long is pretty close to Chicago, so I'm going to get Chicago as the result. Well, let's say I made that 1,000,000 meters or 100 million. Well, and I did the same search again. Now I'm going to get back to Chicago and Manhattan. And this thing is fast. And it's not fast necessarily because of us. It's actually fast because of what Google did. But it's really neat because if you need to do quick lookups, say, I want all the facilities in downtown Chicago, which for us used to be a very expensive calculation. We used Postgres to do it, and PostGIS. We can now do this without having to talk to a database, without having to talk to anything external. And these lookups happen sub-milliseconds. So now that we've talked about all the cool things we built, what does this actually bought us? Well, one Go server can do more requests per second than 150 legacy nodes. You guys probably already guessed. But I just wanted to hit that home again. And search has become the standard bearer here at SpotHero for all of our new services. We can do 200 requests per second with one node. 200 requests per second plus. I'm not going to give the exact number. It's really high. And this is, by the way, this is a very conservative number. Our load testing has shown much higher than this. One web server, horizontally scalable. Unlike our previous solution where we could get to 150 nodes, and if I double it to 300 or 600 or 900 or whatever, it didn't matter. 150 was the now I can keep adding nodes until we run out of Amazon quota. And I can get more quota and keep adding nodes. system will just continue to scale. Also deeply instrumented. Like I said, we have Jaeger, Prometheus, Snap, yada, yada, yada. So if you want to know about any kind of request that happened in the system, you can go and find it. So, if I want to see what somebody searched on Sunday at 3 p.m. and why did it crash, I can literally go find the trace. I can find that error. I can then go correlate that trace to the logs. I can find every single log in our system that was related to that trace. I can even go look at Prometheus metrics from that time period as well. So I'm pretty happy in that regard. I've also changed this from green to red, or red to green, as you can see. 0% request failure rate. We pretty much have a perfect record with this new service. It's not actually 0, but so basically statistically insane. We have a 10 millisecond response time, mean response. So again, 16 seconds is what we were after. Done at 10 milliseconds on average. And this actually has to do with a bug in Go 112. It's milliseconds. So when Go 113 comes out, we expect it to go back down to 5. I linked to that issue. Go GitHub if you're interested in learning more about it. So I also just want to talk about how much money this is. Go ahead. Sorry. We're using essentially, I think we're running, what is it, E4 XLs, I think. But we're running, everything is in Kubernetes. So I'm trying to remember what our pod allocations are. I want to say it's like 8 gigs of RAM. So it's not insubstantial. Big. We haven't necessarily, at this point, here's what I'll say about this, is that we really haven't necessarily done this yet, because with Kubernetes, you can flex how much resources you need, right? So if let's say I change that from, to 1 gigabyte of RAM and 1 GPU core, we would then have more pods that have more throughput than a handful of larger pods. At this point, this has been out for a couple of months, so we haven't necessarily done all this. That's currently where we're at. So it's significant, but it's not, it's nothing special. Commodity. Okay, so how much money have we saved by doing this? I'm not going to give the exact number. I mean, I think it's a little sensitive, but basically, we could pay the monthly mortgage on a multi-million-dollar house with how much money we're saving every month. We could buy Model S we could actually buy a couple Model S's every year, if you're not familiar with it. We could take a monthly vacation. Every month we could go to, like, I don't know, take a 2-week-long trip to some exotic island somewhere. We could do all sorts of fun things with all the money. Fortunately, the money goes back to the company. In any case, we're saving a lot of money. We've also done some really cool stuff. Like I said, we really have upgraded our observability. So I actually want to show you these dashboards and what it looks like from our perspective. So I'm going to jump out of the presentation mode here for a second. And this is actually our live dashboard. So this is production. And you can see that our integration here is pretty cool. So you can see we've got our FX score. You can see our average response time. We have this. This is one of my favorite things. You can actually see the histogram bidding by basically response time over time. So pretty neat. And then as we go down, you can actually see we've been able to break out by those components that we've been talking about. We talked about blackouts and grayouts and so on and so forth. We've actually broken out by each component how much time are our Go teams spending calculating each one of those things. So when we want to target, we don't have this big outlier here, right? Well, what is that? Okay, it's only 3 milliseconds, but why does it take 3 milliseconds? We can actually click on that to isolate it. So a lot of people in the room, this might be old, but to us in SpotHero, this is sort of the foundation of what we do every single time. We're a startup. We're getting out of the phase of not having this. And then really, obviously, since this is a Go meetup, I'd be remiss without talking a little bit about all the Go metrics that come out of the box. The Go Prometheus, which you can see down here. You can see heap, stack, and this is Grafana and Prometheus. If you're not familiar with it, I recommend you check it out. Really important tool for us. And we also have Jaeger. So I'm going to zoom in here a little bit. Is everyone here familiar with distributed tracing? Is there anybody who's not? Show hands. Okay. So distributed tracing is really nice technology when you're working with more than one service. So let's say someone comes into SpotHero.com with the search engine, right? Well, there's not just one application involved anymore. There are a series of applications involved. So if something fails and I don't have this trace, I don't know why it failed. It's like a big black box, right? So once a request has come in, we need a way to figure out if it fails, where it failed, and why. Or if it's slow, why it's slow, and where it's slow. So you can see here, I'm going to expand this guy again. This is our monolith. This is actually, right now, we're still porting all of our existing clients, Android, mobile, iOS, and web to this new API. But you can see here that this thing is still pretty slow. But once it leaves the monolith actually calls this new search service. So if I minimize this, you can see this is our new search service. So you can see how long each. I can do this on a per. What's that? Yes, thank you. Is it a little easier to see now? Sorry about that, guys. You can actually come in here and see now on a per component basis how long are things taking. And so this is another great thing. So if we had a client call up, say, I don't understand what's going on. The search page is taking 30 seconds to load. I can actually say, we can go in the logs and try to figure out, well, what's this person's user ID if they have a user ID. I can find the traces that basically what we call a correlation ID. And then I can go into Jaeger and search by that ID and get to the trace. And I can even see, I can click on these components here and get, we don't have any tags, but I can get the tags and so on and so forth. So I can recreate that request and dig down into the nitty-gritty details of why it's. All right. And I want a few more things that we've grown to love. If you haven't used pprof with Go yet, it is a really nice tool, and it has great integration with NetHTTP. We use pprof all the time to debug performance issues in our applications. Specifically, Brian, who's sitting back there, has used this tool to great effect on a number of occasions. So you can see call stack, you can see the hot call paths, you can see where your code is spending most, where memory is being. This is actually how we determine that Go 112 was causing performance issues for us. We also love that Go emphasizes table-driven tests. If you haven't used this style of testing, I think this is actually a really nice thing to do in Go. So you can actually define a series of tests in basically this anonymous struct, and then you can have a list of the types of tests you want to run, and then use a for loop to just run over them really nicely. So it makes it a little easier to read your tests and sort of reuse the actual testing itself. We also, I know package management and Go modules are a little controversial in the community with the change from depth to Go modules. Go has not necessarily been as smooth as everybody wanted, but we have taken the plunge on all of our Go internally, and now that we have, we really like it. It's really easy to get started. Basically, if you haven't done it yet, you can find this go.mod file. If you add a module, which version of Go you want to use, and then you just write your Go. You import the stuff you want to use, and then when you go build, you go test, it will go off and do the dependency resolution really fast, especially if you've been using depth. It's much faster than depth. And it will go ahead and create that, it'll populate this module file. So I think this tool is really good. It took Go a little while to get here, but now I think that if you're willing to start using this tool, it really brings Go in line with the best modern tools out as far as package management. Upgrading versions is fast and painless. If you've upgraded versions, we're doing Python 2 to 3 with a couple of our internal applications right now. Not an easy process. On Java, say 6 to 8, 8 to 10, not necessarily easy. And every programming language is a little different, but we've gone from way back in the day from 1.7 to 1.12, and it's never taken us more than kind of crazy. We'll see the announcement go out like, hey, Go 1.12 is out, and then as soon as those Docker images hit Docker Hub, we are basically just changing the number and Docker 1.12. So obviously test our code and so on and so forth, but it's pretty amazing dedication that the Go team has to consistent conversion. I want to mention a few things. Obviously, like you guys have probably heard some of these complaints before. I've already talked about the Go 1.12 performance issues. Some of the issues you have with Go is a small pool of developers, which is why we're hiring. Come talk to us. That's something that's a little bit hard for us. Like we want to hire somebody who has experience with Go. It's not the easiest process today. I think that's going to change rapidly here, as you can see, a lot of people in this room. And then, of course, everyone's heard this before. Oh, there's no generics. No, error handling is not what we want. And of course, as we all probably know, Go 2 will bring a number of those features to the table. Some of them may even make as some other features from Go 2 have actually made their way to Go 1. What's next? Well, we're already building a whole bunch of internal tools. We have a handful of things that we're going to be open sourcing in addition to what we've already talked about here. So we're excited about that. We look forward to talking about it in the future. But Go is now sort of a permanent feature of SpotHero, and will really become a part of everything that we build right now. Not every service, but most of it. I'm really excited to be part of the community. We look forward to hopefully having many more of these talks. Again, hiring. If you like this talk, if this work sounds interesting to you, please go check it out or come talk to me. Anybody from SpotHero. Talk to Julia in the back there to raise your hand. I'm really excited to talk to you. All right, questions? Sure, shoot. Yeah.
Hi, so in the beginning you mentioned a lot about where your data was stored. You mentioned RabbitMQ, Redis, and then Postgres. What does the new architecture look like? That was kind of absent from the presentation. Are you still seeing bottlenecks on the database level or in your cache? And I know Kafka is probably, like I'm wondering, was there just stability issues that you wanted to move Kafka for? Or are you also getting performance improvements from that?
All right, great question. So you still, behind the scenes, Kafka is connected by Kafka Connect to our old Postgres database. So with this new architecture, Celery, by extension RabbitMQ, and Redis are no longer part of the architecture for the search problem. We're still using them elsewhere in other parts of our application, but our usage of specifically Redis at least is much less problematic. So we like Redis, we want to keep using it, but we're no longer using, with this new service in place, we're no longer using it. How this actually works though, and the reason that we chose Kafka, is that what Kafka Connect does is it runs periodically and it will actually query the database, say query our Postgres database, and will turn the data that's sitting inside of those rows and tables and so on and so forth into Kafka messages, right? And what's nice about this is that because the search doesn't have to be perfectly accurate, eventual consistency is okay for us. Turns out, kind of a long story short, it turns out it doesn't need to be like an ACID compliant application. No financial transactions are occurring necessarily because of there's a final checkout page where we do an actual do we actually have the inventory? So Kafka is nice because when we start up, we can say, give me all the data that's in each Kafka topic, read all of that into memory in our Go application, and then before we start taking requests, we basically subscribe to those Kafka topics so that any new events that are pushed get pulled into memory. So you could say in a sense that our new search service actually has really the only data store it has is Kafka, and that it doesn't ever talk to a database. So everything is in memory. So if a server crashes or we want to scale a new one in, every single server has to go through that process.
So then by definition, your whole data set can fit on an 8 GB node in memory? That's interesting.
Okay, so that's a great question. So yes, everything does fit in 8 gigs of memory, even less than that, to be honest. And a lot of it has to do, so I didn't talk much about the things we learned from the GPU experiment, but one of the things we learned was how to create very, very efficient representations of the data that we actually need. So what's interesting about that is like a GPU has like at most 6 GB, at least in Amazon timing. And so we had to get really, really slim what we were storing. So we got pretty clever. And today it's not like anybody could like pick up the Go structs and but we basically moved away. In the past in Python, we would just use like strings and objects everywhere. Like, well, we don't actually need that much data. And so really, at the end of the day, the most important thing for us usually is just an integer or Boolean, and essentially those things are fairly efficient in memory. And also, I should say, we don't store things from the past. So search only cares about basically now minus, say, like a couple of weeks out to the rest of infinity. But we don't like store data from 5 years ago. So that actually will. You got it? Appreciate it.
Just out of curiosity, what other things are you stuffing into your context besides your logger?
Okay, so what other things are we putting in our context? Honestly, not too much. Jaeger uses context to propagate scans, so that we definitely use the context for. Otherwise, we don't honestly use it for very much. Really, just the logger. Yeah, yeah. In fact, the developers in the search team have actually had a number of debates about whether we even like context is a pretty hot topic in the Go community. If there's a blog post I think on the Google Go blog about Google everywhere at Google, it's sort of by definition if you're in the HTTP request path, you have to have a context as the first argument to the function. And so when we first got started, we read that and we were passing context from everywhere. We weren't putting anything on the context, but we just thought, well, we're supposed to. Google does it too, right? And then we came to a point where it's like, why are we doing this? We're not really using this for anything other than Jaeger. And so we started to argue about, well, should we just get rid of it? I mean, if you read the debates about it on the GitHub issues reports, people don't like it. They want to get rid of it. And for now, we're kind of have this like what I would call sort of like essentially it's there, but we're trying not to use it until we're hoping that the language your designers come up with better mechanism to pass that kind of down. But for things like the logger or for Jaeger spans, that's sort of what we're. Yes, so the question was, are Kafka and Kafka Connect managed by another company? And so you can't really see, it's actually a small logo. I want to actually do a plug for these guys. I'm not getting paid for them, I get no role from this. A company in Finland called Ivan. They're not, usually people have heard of Confluent. Ivan is like a fraction of the price, and they have the most amazing customer experience. I don't know how many of you guys have ever worked with a software as a service company, but like if we say, hey, we don't like this thing or the way this works, not only will they respond to us like the next day, they'll even tell us like, we put this, if it's a reasonable request, we put this in our backlog. This is when we think we'll get to it, and then our rep will like email us, every 2 weeks or month, and actually give us status updates. Literally, we said we want to use Terraform, Ivan Kafka, right? And we figured, it's not. And then like 2 months later, they built the Terraform provider. We were actually contributing to an open source version of it. They contacted the open source library provider and said, hey, we want to take that over and make it an official Ivan thing. So like they totally listen to the community or to their users. But yeah, we use a managed solution for it. I'm actually a maintainer on the Helm Kafka chart and the Helm scheme registry chart. And so that started part here at SpotHero. But to be frank, running stateful sets and stateful applications in Kubernetes is kind of like a so-so idea. I really recommend it. So that's one of the reasons we abandoned it. But also, we're not a big company. We don't really have we kind of have the no ops philosophy where we want developers to have some ops experience. We do have a couple of ops people who do that full time. But we tend to like developers to have, like it by definition, kind of pushes us towards somebody who is for some more. Yeah, no, I think that's a great idea. Creating snapshots in Kafka. It is something that it's as we continue to iterate on the service, it is definitely like Brian sitting in the back there in the blue shirt, this is like a constant topic of conversation he has with me. Like, how can we like speed up the boot time? How can we make sure that we create these snapshots? Awesome. Yeah, thank you. How long? Okay, so the question was, how long does bootstrapping take? Right now, I want to say it's like what, like 30 seconds, 2 minutes. Okay, well, 2 minutes. I was off by a factor. So it's not immediate. That is something where potentially some of the snapshotting. That is, I think it's actually a really good question because it's actually a major weak point, right? So like if we wanted to scale up 100 nodes really quickly, we could scale up 100 nodes in 2 minutes, but 2 minutes instead of potentially seconds. So we want to get that time down at work. Again, talking about something like CES, right? Let's say that the CES already happened. Let's say that we had another big event come up. We were afraid of like a huge influx of traffic. Well, we want to be able to scale really quickly to accommodate, right? Because if you guys have ever read about like the Pokemon Go, you guys ever heard about this? They use Kubernetes. One of the big first tests for Kubernetes was Pokemon Go. How they gracefully handled their launch. They got, I don't remember, 10x more traffic than they expected. Well, I don't know exactly how they architected their service, but with us, it'd be a little bit more complicated potentially. It takes us a little bit more. So we definitely, I think, to be really future-proof, we really need to. Else? Yeah, this is a great question. So the question was, because multiple things were changed, multiple variables changed, do you really have a sense for what actually contributed to it, right? Like, how do you attribute it? And it's I have to say it's actually a difficult question to answer well, because like you said, variables. I do think that having everything in memory is probably the most important change. If I just sort of hold my hand up and hit the gophers on the screen, that would, I think if I put anything else in there, it'd still be a big, I don't know if it would be fast or faster, but not talking to Redis and not talking to Express was most significant contribution. But I don't, because I don't have the ability to change those variables one at a time, kind of like hold something constant, I can't say that with certainty. My intuition tells me it's probably. The switch to Go is nice. I think more from a developer's perspective than anything else. But I do also think that, I mean, especially compared to Python, Go is a faster language. This problem is not I/O bound, especially when everything's in memory. It's a compute bound problem. So the fact that we're using Go, which is significantly faster than Python, hopefully no one thinks that's too controversial. But relative to say like Java, like Go and Java are close enough in the same ballpark that like I wouldn't feel comfortable saying that it wouldn't have been nearly as performant, more or less. Yeah, the development time is definitely significant. In fact, early on the question was, how about development time? How did Go impact that? So I will say that from my perspective, that our Go projects tend to move very, very rapidly in comparison to any of our other projects. So especially with some of I talked about that SpotHero tools library that we have. We've sort of any decision that a developer needs to make on a web server has sort of been made like what we consider a best practice decision, and any developer can override that setting, but like sort of to basically get an application, the Kubernetes deployment can go out to production is literally have a one-line command to do it. You can start from there, then you can build on. So I think that SpotHero, that Go has definitely helped SpotHero move more quickly. I also think the fact that like we don't have to like say we want to get coverage on our tests. We want to make a decision about how to build our code, things like that. Those decisions have essentially already been made for us. So there's no, like every time we start a project, there's no developer like, hey, I really want to try out this new build tool, right? So like if this was a Java project, I think one of the things we run into in the past, What about Gradle? What about even whatever? Or which code standards should be used? And it's not like meant to be like a significant knock-on, but it does make a difference, right? We don't have those conversations to go. The fact that the library, or sorry, the fact that the language is also really tiny, 23 keywords as people like to say, means that it's pretty quick people pick it up. Had people come onto the team and very rapidly productive on Java, right? So we've been, some capacity or another, trying to sort of onboard people into the JVM ecosystem, specifically Java, a couple of years, really sort of mixed how quickly developers absorb that ecosystem and produce quality result where it can go. We have a much smaller sample size, so it may not be scientifically significant, but I will say that good luck. It has made a difference. The question was, what was the main problem when we switched from Python to Go? Everything sounds great, but there's got to be some issues. So let me think about this for a second. So I'd say the first thing is that it's not necessarily a Go problem, but just at the time when we started working on this project, the people who had worked on the original version of this algorithm had long split. And I think we underestimated how complex this was, but they actually done a pretty good job of what they had of solving. As far as moving to Go, I think that some of the things that threw us for a loop initially, package management, was what did everybody use before? Not Go vendor. What did it? Get the name. It might come back to me. Anyway, we switched package management solutions, expense management, and it was kind of confusing. Like at that point, the landscape was a little bit more for us as far as like what should we actually be doing. I also think that obviously the fact that Go is not as easy to modify as far as testing is a little more difficult for us. So let's say like I want to write unit tests, I have to actually think about with Python. I don't think about testing. I just write the code and then I'm like mock this, mock that. This function call doesn't exist anymore, or this function call does whatever I tell it to do. With Go, you can kind of get there with your own code. But if I'm using someone's library, that library doesn't have, like let's say it doesn't have a mock version of itself, or someone has built a mock version of the interface, it can kind of produce work for us. There's also the issue of sometimes when we were first getting started, especially, we just didn't understand. We knew how to write Go pretty quickly, I think, but we weren't necessarily thinking about like how are we really going to create unit tests that aren't just following this like series of. So it took us a little time to figure it out. And we were actually on this project early on. We experimented with TDD, test-driven design. So that was something that was kind of interesting because we would write these tests and thought we were doing a great job at actually writing integration. That was a big struggle. Can you ask it one more time? I'm not sure I understand. I see. So the question is, given that the type system, we feel like we have to unit test a little bit than we would in Python. And the answer is, yeah, definitely, that's the case. If you've written Python or Ruby, I haven't actually written much Ruby, so I'm sorry if I'm misspeaking, but I think it's similar enough to Python that I can say this. With Python, we would write unit tests all the time that were just like, if I call this function that expects an integer and I pass in a string, what happens? If I pass a none into this function, it doesn't expect it, what happens? Like, I don't do that with Go hardly ever. Sometimes with nulls or nils, you'll write kinds of tests, but yeah, definitely, given the fact that it's compiled language plot, and it means that we're writing a lot less tests than we might have done. Another great question. So the question is essentially, if we have multiple events coming in at the same time, we have all these go routines going on, how do we actually protect, how do we make sure that we're getting the right data? How do we protect it given that we have all this work going on at the same time? As far as the ingestion from, say, Kafka, for example, we actually do have using brain. Why can't I think? Mutexes, yes, thank you. Using mutexes on the data collections, actually like lock very briefly, and then update the collection, and then unlock. What's nice about this is that it actually, like I said earlier, most of our data changes fairly infrequently. The only thing that is really the exception is that of reservation. And reservations happen pretty frequently, but not frequently enough that it really impacts performance. What's interesting about it too, what we found, this is sort of a SpotHero business insight, if you will, most of our parking operators are not actually as inventory sensitive as we. So when we started the company, I wasn't actually here, but when we started the company, they said, if we have 10 spots, we can only sell 10 spots. Well, it turns out, strangely enough, that and except for a handful of parking garages, that our parking operators are really, really flexible. They actually don't necessarily mind selling 11 instead of 10, even if they only have 10 physical 10 line spots. They're like, oh yeah, don't worry about it. We'll find a spot behind these cones over here and make it work. You know, it's income. So we actually can leverage some of the. This is kind of one of those cool things where you can actually look at how does our group. And we've learned this now from actually doing this for a while. It's actually okay for us to not to be eventually consistent. So even if, say, we got rid of that, we have it today, but if in the future we get to a point where this would be an awesome problem to have. We're making so many reservations that it actually does impact performance. It'd be okay. I think our operators, for the most part, would be okay. Question. Okay, yeah, so the question was, does each city get its own search instance? And so if I could show you like the roadmap of where we want to get eventually, yes, but today, no. Today, actually, we do have a number of servers running, but because of basically the huge improvement in throughput, we don't have that many servers running at all. But actually, one of the things we talked about with the Redis configuration way back in, we actually talked about like, well, what if we had a Redis per city? Because people aren't typically searching the same, you know, you're not going to be searching Chicago and New York. So that was something we did POC it, and it did help a little bit. We never, because of the progress we were making on this project, we never actually realized that it wasn't necessary before this came out. But it is a thing that I think someday, hopefully, people continue to like our product that we will. And actually, if you're interested, we talked about geo-collection. Uber has a really awesome blog post about their geo-location lookup for how they do it, and that was actually one for us. Maybe I'll add it. They've done a lot of amazing work, and that's something they do. So they actually will have basically localized, city-based, even sometimes neighborhood-based lookups. So it's a really clever solution. Yeah. So the question was, there are a handful of portions. If I miss anything, let me know and I'll answer it. This is a great question and actually points out something I forgot to mention. So I'm going to go back to Jaeger for a second. And I'm going to minimize this. But the question essentially comes down to why is it so slow? If I go to SpotHero.com/search, it takes ever. I said it was so fast. Why is it slow? Well, there's a bit of an unfortunate fact. It is a temporary thing. So I'm going to show everybody. He's not wrong. If I go here, I refresh, right, or not. Okay. If I refresh, It's gonna take a while. Page is now loaded, but like sitting here, come on, I mean, I could make myself a cup of coffee and take a jog around the block. Like, what the hell is taking so long? Well, it turns out what the hell is taking so long is that unfortunately, not all of our clients have been updated yet to work with the V2 version. So what's actually happening here is that, I'm going to go back to Jaeger now. When the request is made from the web server, I'm sorry, from my computer, the client computer, to our web server, it's actually hitting the old monolith, Python Django. The Python Django application is painfully slow, even when it's not doing anything. And so you can see here in this Jaeger trace, at the left-hand side over here, we have 0 milliseconds. It goes all the way up to 161, which isn't 10 seconds. But remember that we're making about, how do I keep open? Anyway, we're making, what's that? We're hiring. It makes a number of requests in circles. And so each one of those requests takes an increasingly long time. And so what's happening here is, if you actually look, I swear that was not intentional, I swear. If you look here, this yellow dot that says 3.11 milliseconds, this is actually the call to the new search server. All of that blue, the old monolith. And so that's really the problem. So we're upgrading right in the process right now. Basically just trying to get time scheduled for Android, iOS, our mobile teams to our web teams to upgrade to use our new V2 API. Why wasn't it immediate? Well, actually, maybe I'll show you. I think the easiest way to describe why would it just take such a long time? No, I don't want mail. If I go to network, I'm going to filter by XHR. I'm just going to refresh the page real quick. And I'm going to show you how crazy the responses to the V1 API are. This is it. Here we go. All right. So this is just one of a handful of requests that we made. The number of results here, I'm just going to expand the first one. There's a lot of data in here, a lot of data. It turns out that none of our applications actually use any of this data. The only thing they really care about is how much does it cost and where is it located, right? And like, what is the image? And so when they built this back in the day, they're like, look, we're just gonna, you don't know what our clients need, so we're gonna put everything. Anything we can possibly think of. We actually kind of made our own like mini GraphQL thing, query parameter called includes. And so each one of these requests is making a super gnarly set of database queries. And that's really what contributes all this time. So if you talk directly to our search endpoint, so I'm gonna do that real quick. If I go to our facility, I'm gonna go to this is a VPC private endpoint. So unfortunately, you can't just use real internet. But boom, that was, I don't know, 1,000 results. I'm gonna refresh this again with no cache. So I'm gonna make sure disable cache, right? All right, let's refresh and see how long that takes. So that was 146 milliseconds round trip. That here. So this is what it would take if monolith wasn't involved. So to answer your question about have we tuned servmux, yes, we do time out on less than 5 seconds, I think. Basically, what it takes us a long time to respond, which is we have not looked at fast HTTP or other libraries we've talked about. We may eventually. We've also talked about, hey, should we look at using like the fast JSON libraries? And we talked about, we just haven't done it yet. We're just using the built-in functionality. But yeah, I'm hoping like next time that I give this talk, you know, I can just show this with the actual website because it's like super. It's a huge bummer to refresh the actual web page and see it take forever. Well, this guy said all these cool things, but it's actually not fast. Well, unfortunately, it's still not fast here yet, but it will. Thank you for the question. Great. Anybody else? On a city-by-city basis? I'm sorry, can you state the question one more time? So one of the things that we talked about with the original algorithm, atomicity, used Lua to solve that problem. Well, it turns out that we just sort of didn't, the original team didn't necessarily understand that actually. One of the things we found during our investigation was, look at all these compromises we made for atomicity, then those things actually, our operators don't actually care. Like if our results were, by the way, they're wrong very infrequently with this eventually some like fraction of a time, and we're comfortable in those cases. Popping up an error to a user. We've even talked about saying when those things do happen, just like giving a credit, saying, hey, we're sorry we screwed up. And so from our perspective, the sort of trade-off in terms of infrastructure and speed is worth it. To just apologize to a customer and say, we're going to make it. And the way that we'd screw that up is we'd either oversell, make it rejected at a garage, in which case we comp the whole thing and give them probably credit and the full and a park. But if it's like you get to the checkout page and we've oversold, at that point, that's probably where we just sorry, how about this? So the way that we address that is, we address this way in the old system is like, if I click out of here, let's say I want to book this parking spot, I'm just spot. I click this. While the page is loading, at this point, we're talking to the database, making sure that we actually have this. But the thing that's kind of hard about this is that even if we wanted to make sure this was available, we'd have to build a product like Ticketmaster. Ticketmaster actually like locks, right? And they hold on. It's like a 5-minute lock. It's hard to build a system like that, right? We don't have it. We've never had, and we don't have a system that does that. So even though we did a database check here, let's say that, like, I don't know, let's say you went and booked this spot, right? And I didn't refresh the page. Let's say I went on, I got a cup of coffee, I came back. In the meantime, you booked the spot, which is a black spot. When I go down here to click pay and reserve, I'm going to get an error saying, sorry, we screwed up, or we sold the spot. So there's actually, right now in our system, we don't even have, even if we still use the Redis and Lua system, we don't really have a way to prevent or giving the customer potentially a bad experience. Maybe someday we'll build something like Ticketmaster, but it's kind of a question of like, is it better to apologize to the customer the times those happen and give them a credit, give them some incentive back and realize that screwed up, or is it better for us to build this really complex sort of like inventory locking? Right. Else? Cool. Oh, one more? No? So, you can ask me after. I'm happy. Yes. So with locks? Oh, logs. Logs. Yes. Great question. With Zap, logs to standard out, because we're running in Kubernetes, what happens is standard out from the pods gets captured by FluentD. We have a FluentD that runs on every single node in our cluster, and FluentD then exports those logs out to Sumo. Sumo logic. We'll go, I'll just plug these guys, I guess. I don't know why. They're kind of expensive. They have a really great product. If they have really cool UI, it's kind of like Elk, the Elk stack. If you guys are familiar, it's just their own thing. They have map reuse for logs. It's kind of neat. But yeah, we funnel out to this. If you were running the Elk stack, or you wanted to send the logs to Kafka, you could just as easily do that.